It's often very handy to know the Fourier transforms of some elementary signals. Let's start, for instance, with the impulse or direct delta, delta t, which is 0 for all times t which are not 0, and goes off to infinity for time t equals 0. The Fourier transform x of omega is equal to the integral between minus infinity to infinity of delta e to the minus j omega t dt. This could be rewritten as the convolution of delta and e to the minus j omega t evaluated at t equals 0, and hence we can use the property of the convolution integral, which tells us that this must be equal to e to the minus j omega evaluated at t equals 0, which is 0, which gives us e to the power of 0, which is equal to 1. So in the frequency domain, the Fourier transform can be expressed as a constant. If, however, we have a constant in the time domain, this is x of t equals to 1, for instance, then by duality we know that x of omega is 2 pi times the direct delta as a function of omega, which is 0 for all frequencies omega up until 0, then infinity for omega equals 0, and 0 again for all positive frequencies. As we know already, taking a rectangle in the time domain, which is centered around 0 and has width tau, so that it's plus 1 for times between minus tau half and tau half, and is mathematically expressed as the rectangular function of t with pulse width tau, then the frequency response is the sinc function with height tau for omega equals 0, and 0 crossings at multiples of 2 pi over tau. If we have a rectangular function in the frequency domain centered around frequency equals 0, which is 1 for all values of omega between minus omega 0 and plus omega 0, such that x of omega is equal to the rectangle function of omega with width 2 omega 0, then we know that in the time domain x of t has to be a sinc function of the argument omega 0 t divided by pi, scaled with omega 0 divided by pi, which is a sinc with height omega 0 divided by pi for t equals 0, and 0 crossings at multiples of pi divided by omega 0. We can also calculate the continuous time Fourier transform for periodic signals. For this we can use the fact that for periodic signals x of t, the Fourier series expression exists, which tells us that x of t is equal to the infinite sum for n equals minus infinity to plus infinity of the coefficients dn times e to the j n omega 0 t. Taking the Fourier transform of both sides of the equation gives that the Fourier transform of x of t, which is often written in this form, is equal to the Fourier transform of the Fourier series expression. Since the Fourier transform is linear, this is equal to the sum of the Fourier transforms of e to the j n omega 0 t, weighted with dn's, for n equals minus infinity to plus infinity. Note that the Fourier transform of e to the j n omega 0 t can be written as e to the j n omega 0 t times the Fourier transform of 1, for which we know that the Fourier transform of this is 2 pi times the direct delta of omega. Also using the frequency shift property of the Fourier transform gives that this must be equal to 2 pi, a shifted version of the direct delta in the frequency domain, which is shifted by n omega 0. So the frequency response of x of t, or its Fourier transform, is an infinite sum of shifted direct deltas to the multiples of the fundamental frequency omega 0, scaled with the Fourier series coefficients dn, and overall multiplied with 2 pi. Let's consider the example x of t equals 3 times the cosine of omega 0 t. Using Euler's formula, this can be expressed as 3 divided by 2 times e to the j omega 0 t plus e to the minus j omega 0 t. This is already the Fourier series expansion of the cosine, and it shows us that the Fourier series coefficients dn are given by 1.5 for n equals 1 and n equals minus 1, and 0 otherwise. Drawing the coefficients dn as a function of their index n shows that for n equals 1 and n equals minus 1, the coefficients are equal to 1.5 and 0 for all other values of n. From the formula above, we know that the Fourier transform capital X of omega is equal to 2 pi times the infinite sum for n equals minus infinity to plus infinity of the dn's times shifted direct deltas, so that x of omega is equal to 2 pi times 1.5, which is the first coefficient for n equals 1, times the direct delta as a function of omega shifted to n times omega 0, where n now is 1, so that we get minus omega 0, plus 1.5, which is the value of the second coefficient for n equals minus 1, times the direct delta of omega, minus n omega 0, and n now is minus 1, so that we get omega plus omega 0. Simplifying this slightly gives that this is equal to 3 pi times the direct delta of omega minus omega 0 plus the direct delta of omega plus omega 0, which in the frequency domain has a direct delta at minus omega 0 and a direct delta at plus omega 0, and both are scaled with the factor 3 pi.